The next case to consider is the case where the Q factor is a half. What's interesting about this one becomes apparent when you try and work out where the poles are. This is our general form for the denominator of our second order system in terms of the resonance frequency and the Q factor, and the poles are the values of j omega for which this is equal to 0. If the Q factor is a half, and I multiply up by omega naught squared, then I would end up with this expression here. And you might be able to recognize how to factorize this. That's just j omega plus omega naught squared. So our two poles are coincident. They're at the same value of j omega, at a value of minus omega naught. And that makes the amplitude response very simple to sketch. We're going out at 0 dBs until we get to this point here, the resonant frequency, at which point both poles switch on, and according to the Bode approximation anyway, and the output plummets at 40 dBs per decade from then on. Log of frequency. And that's it. A particularly easy case to sketch the amplitude response for. The amplitude response looks like this. This is the actual amplitude response. Our sketched approximation we've just done. In terms of the phase response, both of the poles are causing the phase to change at the same amount. So what we have is something that looks very much like a single pole's phase response, except it's exactly twice the magnitude. It drops from 0 to minus 180 degrees over approximately the range of frequencies from the pole's break frequency divided by 10 to the pole's break frequency times 10, in this case from 1k to 100k. And that's it. When we get on to deriving the step response of these circuits, we'll find that this particular case of Q equals a half causes some real difficulties. But for the amplitude response, it's really quite straightforward. Right, that might be a record for the shortest of these videos. Next time, we'll have a look at very large Q factors.